In this sequence of videos, we're actually getting into a different type of material than we're used to. Up until now, and frankly the vast majority of AP Physics 1, it's dealing with solids, or something physicists called rigid objects. It's just things that retain their shape. We've always been talking about blocks, or wheels, or just cars acting as simple solid objects, but we're going to get into liquids and gases, and there are a lot of similar force topics, but they're almost like cousins. For liquids and gases, we are dealing with some alternate topics that are related to some of the things we've already learned, but almost specializing for now this type of material. So to get us started, we're going to look at density and pressure, two things that frankly you can use for rigid objects, for solids, but we'll also see them applied a little more directly, a little more explicitly for liquids and gases. And then we'll look at this whole thing called fluids anyway. But anyway, let's go ahead and get started, okay? First item of business, all right? Team, density. Here is a new word, a new definition, and yes, a new equation. The density of a material, it's based on how much mass there is within a given volume. So it's not just looking at how big or how massive or how much inertia an object is, it's how well that object, or maybe how compact that object is, contained within a certain volume, okay? There's actually an equation for density, which we'll get to in a second. For example, on this little image here, this is representing gold. Gold is a very dense material. Over here, this picture is meant to represent feathers. Feathers are a much less dense material. Now, there's kind of a classic question. It's like, oh, which weighs more, a pound of gold or a pound of feathers? And team, it's a trick question, because if you have 1 pound, or let's say 1 newton of gold and 1 newton of feathers, that's the same thing, okay? It's the same amount of force. But what it's really trying to get you to think about, or maybe recognize, is 1 pound of gold, or let's just even say 1 kilogram using mass. 1 kilogram of gold is not that much gold, but if I wanted a kilogram of feathers, oh man, I would need a lot, because feathers have a much smaller density, all right? You would need a huge amount of volume to compensate to get the same amount of mass, or to get the same amount of weight, because it's just m times g. But density is based on mass and how much that mass is compacted, okay? The equation is pretty straightforward, though it is a symbol that you may not have seen before. Density is equal to mass divided by volume, or using symbols, the symbol for density is lowercase Greek letter rho. It's not exactly a P. This is how I would draw a P. Rho symbol, Greek letter, is almost like an italicized, kind of a fancy. I almost do it like the opposite of a P. Instead of doing the vertical line then the loop, I do the loop and then I end with the vertical line. But that's lowercase Greek letter rho. Careful, don't call it P, because that letter is used for something else later. But density is equal to, well, this is pretty easy. Mass is still m. We've done that before. Volume is still v. Okay, or maybe I actually should say volume is v. I don't know if we've ever actually used volume before. This is like geometric volume, okay? Careful, this is not recommending, or I'm sorry, this is not showing velocity. The units for density, well, team, there's a basic idea that I've probably said before. The units have to be the same thing as the equation, all right? For my equation, it's mass divided by volume. So the units for density, well, the unit for mass is still kilogram. The unit for volume, the volume of something, that's base times height times width. If we're using m still for displacement and distance, and yes we are, that means volume is going to be meters cubed. You would read this as kilograms per cubic meter, or kilograms per meter cubed. There is no special name for this. So if you were asked to calculate density, this is what you would write down: kg divided by m to the third power, okay? Obviously with this equation, maybe you could solve for mass. If you knew these two things, you could maybe solve for volume, all right? But that's the basic equation for density. Can be used for solid objects, of course, but also we're going to see it used, or at least it's going to pop up from time to time, looking at gases and liquids, okay? Second main topic, all right, that's pressure. Just like for the last one, we were kind of looking at a special case of mass, something we learned before. Pressure is us kind of looking at a special case of force, something that we learned before. And there's a classic example over here. Let's say this is the same person, okay? They're wearing maybe different shoes on different feet. Let's say this person has a weight of 120 pounds. I know I'm not using newtons, but we're all familiar with pounds. Let's say they weigh 120 pounds, and this person accidentally steps on your hand. If they step on your hand with this sneaker, it's maybe not pleasant, but it's likely not the most painful thing, because this object here, this sneaker, has a large area. When something with a large area applies a force on, say, your hand, you're absolutely going to feel that, but the sneaker with its large area kind of spreads that force out. Versus over here, and oh man, let's just say they step on your hand, oh gosh, it hurts just thinking about it, with the heel of their high heel shoe. This is a much smaller area, and man, that applies much more, it turns out, it's pressure. Our nerves in our hands, everybody, yeah, you could kind of say they feel force, but really they are reacting to pressure. So if you have a certain amount of force over a much smaller area, it turns out that's a much larger pressure, which is what your nerves are sensitive to. The equation for pressure is pretty easy, just like the last one. It's force divided by area. Now, we've learned about forces, pushes and pulls. Area area is, base times width, all right? P is what we use the symbol for pressure, okay? Pressure is equal force divided by area right there, okay? Now, in terms of the units, if I ask you to calculate pressure, what unit would you use? The unit for pressure, again, has to match the equation. So it would be something divided by something. The unit for force, that's newtons. Divide that, because I have this division right here. The unit for area, again, if it's like length times width, that's going to be meters squared, newtons per meter squared. You could write this down, and it would be totally accepted on any kind of quiz or exam or on the AP test, but this is actually given a special name. Unlike density, which didn't have a special name, this is known as a Pascal, named after a prior scientist. A unit of pressure are pascals, or you could simplify that as PA. So if I said, okay, you're going to take 120 pounds, divide that by the area, or let's say it was like 60 newtons divided by an area of 2, that would be 60 pascals, or 60 PA. That's the unit for pressure. Again, rigid objects absolutely apply pressure, but you're also maybe familiar with the idea of like gases and liquids building up pressure. That's why we're talking about that right now, okay? My last little section. Again, team, what we're going to start really focusing on in this sequence of videos are liquids and gases. We're moving away from solids for the time being, and these three things are the three classic states of matter. Yes, there are in fact more than just three. Plasma, for example, is a fourth state of matter. If you really get into the rabbit hole of modern physics, there are in fact others as well, but we're just going to stick with the classic three: solids, liquids, and gases. Solids are solids just because it means their atoms and molecules are almost locked in place. Even if I applied a force like right here, these things are so locked in place that the whole rock moves as one thing. That's what we've been doing for the vast majority of this class. But liquids, it turns out, still made of atoms and molecules. They are still connected. They still do form chemical bonds, but it's like those chemical bonds are looser. The water molecules can slide around. They're still connected to each other, but imagine them being able to slide around. They're not quite as rigid. And then on the far extreme end are gases. Gases are when the molecules are completely separate. They have little to no bond, so they act as their own individual particle. This is like ice water, this is like liquid water, and this would be like steam, water vapor. It's actually based on the energy of these particles, but that's even a bit beyond what we're going to get into for AP Physics 1. So again, team, we're going to start looking at liquids and gases. Liquids and gases are both collectively known as fluids. Another way you can think of it in terms of liquids and gases are they fill the shape of their container. That's a classic definition that defines how a solid is different from a fluid. If I put a rock in a beaker, the rock maintains its shape. But obviously, if I pour liquid water into a beaker, or if I filled up something with water vapor with steam, it fills or it takes the shape of the container. These are fluids, these materials that have weaker bonds that are able to move around a bit more. So that's it. We talked about pressure, we talked about density, and we just identified what we mean by fluid. A fluid is a liquid or a gas. Admittedly, team, in this topic or in this class, we focus a bit more on liquids, but both are true. Both are fluids. All the physics we're learning in this sequences can be applied for liquids and gases. Okay, oh man, that's enough. Thanks a lot for watching this video.